Embracing the power of prediction. Machine learning is transforming how we interact with technology. It's helping us build smarter products, make better decisions, and even predict the future. In this essay, we'll explore how machine learning can be applied to a real-world challenge, predicting the energy output of a power plant. Imagine being able to anticipate how much electricity a power plant will generate. This knowledge is incredibly valuable for energy companies. It allows them to optimize operations, reduce costs, and ensure a stable power supply for everyone. This essay will guide you through the process of building a machine learning model to achieve just that. We'll break down complex concepts into simple terms, using examples that are easy to understand even if you're new to the world of machine learning. Unlocking insights from power plant data. The first step in building our predictive model is to understand the data. In this case, we're working with data from a combined cycle power plant. This data includes various parameters like ambient temperature, pressure, humidity, and exhaust vacuum. Each of these parameters can influence the power plant's energy output. Our data set looks like a table, with each row representing a different point in time and each column representing a different parameter. This data is a goldmine of information. By analyzing it, we can uncover hidden patterns and relationships that can help us predict future energy output. Choosing the right tool for the job. Now that we have our data, we need to choose the right machine learning algorithm to build our model. There are many different types of algorithms, each suited to different tasks. Since we're trying to predict a continuous value, the energy output, regression algorithms are the most appropriate choice. Regression algorithms are like powerful calculators that can find the relationship between our input parameters, temperature, pressure, etc., and our output, energy output. We'll explore several regression models. Linear regression, the simplest type of regression, assuming a straight-line relationship between the input and output. Ridge regression, which builds upon linear regression by adding a penalty for overly complex models, preventing overfitting. Lasso regression, similar to ridge, but it can shrink some coefficients to zero, effectively performing feature selection. And finally, polynomial regression, which allows for curved relationships between the input and output, capturing more complex patterns in the data. Section 4. Training and testing, preparing our prediction model. Before we can use our chosen algorithms, we need to train and test them. Imagine training a dog. You wouldn't expect it to know a trick without showing it first. Similarly, we need to train our models using our power plant dataset. We divide our dataset into two parts, a training set and a testing set. We use the training set to teach our model the relationship between the input parameters and energy output. Once trained, we test the model's accuracy on the unseen testing set. This helps us evaluate how well our model generalizes to new unseen data. Section 5. The power of K-fold validation. To ensure our model's reliability, we can use a technique called K-fold cross-validation. Imagine folding a piece of paper multiple times and then making cuts along the folds. K-fold validation is similar. It divides our data into K-equal parts or folds. The model is trained on K1 folds and tested on the remaining fold. This process is repeated K times, with each fold getting a turn as the test set. This provides a more robust evaluation of our model's performance as it's tested on different subsets of the data. Section 6. Finding the best fit, comparing model performance. After training and testing our models, it's time to compare their performance. We use a metric called mean squared error, or MSE, to measure how well our model's predictions match the actual energy output values. MSE calculates the average squared difference between the predicted and actual values. A lower MSE indicates better accuracy. By comparing the MSE of different models, we can identify the one that performs best on our power plant dataset. The model with the lowest MSE is considered the most accurate and reliable for predicting the power plant's energy output. This model can then be deployed to assist in energy management, optimizing operations, and ensuring a stable power supply.